He's not showing up.
Can whoever's out there in Zoom,
Or did it bring job?
how do I? I'm just gonna mute these people. That's a good way to make them be quiet. Okay. All right. Okay, fantastic. All right, guys, thank you for moving up. I appreciate that. Let's go ahead and get started here. I hope that you guys are all doing well. We have a homework assignment that's due tonight. It seems to be going pretty well. I've talked to a few people about a couple things on it, but if there's anything more that you're still stuck on, I'm gonna be around all evening. After class, I'll stay around for a while. I'll go get dinner and I'll come back, my usual Thursday night routine again. So feel free to ask me something. You can also come into Zoom. If you don't want to hang around, you want to get going home and ask me something tonight, you can come into Zoom and ask me. But I definitely want you to feel good about all these problems. But what we're going to do today is basically just plow through a bunch more of the basic graph theory material and kind of just get some of it behind us. We'll save some group work until next week and that sort of thing. But I want to talk about first Eulerian trails, and then a little bit later today, we're going to talk about Hamilton paths and cycles. So a couple of topics that I think you guys will enjoy very much. Yeah, so the graph theory is well underway at this point. The definition that I've recapped up here is building off of what a trail is. Remember that a trail is just a walk in a graph that never repeats an edge. So you're not going down the same highway twice. Okay, so no repeated edges. So to remind you here, no repeated edges. That would be a trail. So a trail that uses every edge. So if I use every edge, but I don't repeat any edges, that just means you're using them all once, exactly once. That's called an Eulerian trail. Okay, so we got that. An Eulerian trail uses every edge exactly once. And as we're making these Eulerian trails in our graphs, it really will be helpful. I heard some people saying, oh, it's time to start getting my colored pencils and markers out. Yes, I would highly recommend if you can get yourself a hold of a couple of different colors to help you trace these out, it will really, really help. Because what we're going to try to do is trace the edges of this Eulerian trail. We want to know which ones have we used and which ones haven't we used as we're going along. So it'll just be easier if you have different colors to work with. Let's take a look at, I put a fairly modest example here of a graph, and I want to know whether it has an Eulerian trail or not. Now, some of you probably remember we put the theorem up on Tuesday that already kind of answers this question. But let's just play with it kind of from scratch for a minute and see what we think we can come up with. So if we're going to use every edge, then we could sort of just start somewhere and just start following the edges around as best as we can, right? So you could tinker around with this and you could say, well, maybe I start at A, just because for no better reason than just to start somewhere. And you might say, well, I might go from A to B, right? So this is why I like to have the colored pens, because now I've used that edge, I'm not going to draw it again, right? And then from B, I have to go either to C or D. Maybe I'll just go to C. So I just add that to my little list here, and you just make a chain of arrows and you just draw your trail this way. And I do have to use the edge that goes from C back to A at some point. Maybe I'll just do that now. So I'll go back to A right away. And then I'm going to leave A again on the only edge I haven't used yet, which is D. So what I'm doing is trying to construct an Eulerian trail. Once I get to D, I have to go somewhere. Maybe I'll go to F, okay? By the way, this sort of thought process of creating this trail is going to be helpful for writing up a proof of this characterization about Eulerian trails in a minute. So it'll be something good to keep track of. So I get to F, and then I say, well, from F, I have to go back to C, the only edge that I have available there. And once I get to C, you can see that most of these edges are now blue, so I've already used them. So I have to pick an edge I have not used yet. Maybe I'll go over to E next, right? So I could go from C to E, And then obviously from E, I would then be forced to go down to D. Right? And then, let's see, what edges are still not colored in with blue? Both of these, right? D to C or from D to B. The problem is, if I'm standing here, I can't go here and then get over to this edge. I can't go along this edge and get over to this edge. So it's kind of like we're stuck. Right? Now, the critic is going to come along and say, well, you just didn't start off very well. You shouldn't have started at A, or you didn't pick the right sequence of edges. Disproving an Eulerian trail by just trying to do one for 10 hours and not succeeding isn't a proof. So the temptation here is going to be that the answer is no, but we've got to give the right reason for this. And the reason is going to be due to the theorem below. So I'm going to restate this theorem. I wrote it down on Tuesday at the end of class, but we have not proven it yet, and I want to talk about it a little bit more. So it is due to this theorem that I'm going to lay out right here. Let me shift my camera this away. And so the theorem goes like this. It's 11.2.2 in the book. And it just says, let G be a connected general graph. Let G be a connected general graph. So then G has a closed Eulerian trail. So this is going to tell us when we have a closed Eulerian trail, and the answer is going to be if and only if every vertex has even degree. We wrote that down briefly on Tuesday, but you can see that this graph has, well, there's a vertex of degree 5, there's a vertex of degree 3, there's a vertex of degree 3, lots of odd degree vertices. So this is not going to have an Eulerian trail for that reason. Let's go ahead and write down a proof. A couple people have stopped by my office in the last day or two, just a little concerned that some of these proofs seem just like they're wordy explanations rather than like something really robust with formulas and so on. That is the nature of this. And you're going to see when I write this proof out, it's going to feel more like a conversation than something that might be, that you might see that's using hard equations and formulas and results. So that's just kind of the nature of it. Okay, so let's do the proof. We have to prove this in both directions. I'll go ahead and start by proving the forward direction. Meaning that I'm going to assume that G has a closed Eulerian trail. So let's start with that. Assume G has a closed Eulerian trail. Okay? And I would like to show that every vertex has even degrees, so we have to grab a vertex. Let's call it little v in capital V. So the capital V is the vertex set that we have. And so the claim here is that the degree of V is even. So I've kind of just set up what I need to do. And my claim now is going to be that this vertex has even degree. So we can look at our closed Eulerian trail and we can look at a vertex that is on that trail. And as the trail arrives into that vertex along some edge, it will also, of course, have to continue out of that vertex along another edge, not the same edge because you can't repeat edges. So there would have to be two edges incident with V that are involved in visiting that vertex one time. So I just spoke it all out loud. Now I got to write it down. Okay, so let's write this down. Each time the Eulerian trail I'll just say visits V, sort of means it passes through V. So every time the Eulerian trail visits V, two distinct edges, two different edges. Two distinct edges are used. Okay, and so if V is visited K times, if we visit that vertex K times, then let's just say, sorry, let's say if V is visited K times by the closed Eulerian trail, then we actually can say that the degree of V is actually going to be equal to 2K. Because every edge has to be used exactly once. And so if I have managed to arrive and then depart from V K times, I will use two different edges each of those visits. So in total, 2K edges will have to be incident with V. And that's all of the edges that are incident with V because you have to use them all. The closed Eulerian trail by definition uses every edge, right? So that's that is the point. Does that make sense? Anybody? But again, it sounds more like a conversation, right? You're writing out sentences and kind of just describing it a little bit conceptually that way, rather than using any particular formula. So that's just the nature of the beast. This is kind of the way that the argument is going to look. Okay, so far so good. All right, so we also have to go backwards. We have to assume that every vertex has even degree and then try to prove that G has a closed Eulerian trail. And we're going to do that by actually constructing the trail. So one way to prove that something exists is to actually make it, to construct it. And when you're constructing, and just as we were doing on this example, when you're constructing this closed Eulerian trail, you just sort of have to start somewhere and then just start rattling off edges and see what happens, right? So let's do that. Let's choose a vertex to start at. Let's just choose it. I'll call it V naught. So this is just any vertex in the vertex set. We can actually make that an arbitrary choice. Some of you might have been wondering, well, does it matter where we begin when we're making these trails? Turns out it doesn't. For this Eulerian trail, at least not for the closed Eulerian trail, it's not going to make any difference where we start. So this is totally arbitrary. We can't make a wrong choice here. Just pick any old vertex that you want. And then what you're going to do is just grab any edge that's coming out of that vertex. There has to be one, because if there's no edge coming out of V naught, then V naught is an isolated point and your graph is not connected. There has to be an edge there. I'll call it E1. So let's choose any E1, which is some edge. I'll write the edge as V naught going to V1 in E. And let me just add that this must exist since G is connected. Connected means you have to be able to walk between any vertex to any other vertex. So if there was no edge here, then we wouldn't be able to walk from V naught to anywhere, right? It'd be impossible. So that's just kind of clarifying that a little bit, that we have to be able to do that. Okay, so I'm gonna have to come over to this next board to write the rest of this out. Is everybody with me so far? So far so good? Okay, great. Now, V1 is now being visited for the first time. We've grabbed an edge and we've headed into V1, but the degree of V1 is even by assumption. So there's at least some other edge not used yet that we can now leave along. The nice thing about this algorithm, guys, is you don't have to turn on your brain. Like, you can't mess this up. You just choose any vertex, choose any edge, then choose any other edge. You just keep playing this game and you can't really like boil it up as long as you don't repeat an edge, okay? So I'll just say, since the degree of V1 is even, we can choose another edge. Let me call it E2, which would be starting from V1 and going to a vertex V2 this time, in the edge set. And this is with E2 not the same edge as E1? Now, it would be possible for V2 to be equal to V naught again. That would be possible because this is a general graph, which means you're allowed multiple edges. So it could have been, right, so you could have had V naught and then here's V1, right? And you just took this edge E1 and now you're taking this edge E2. There wouldn't be anything wrong with that. Totally okay in this context. Okay, so at any rate, we end up at V2, which may or may not be the same as V1, and we're just going to repeat this process. So you just kind of keep doing this, you get to a new vertex, and since you just arrived on some edge, you have to be able to leave along some other edge because the degree of that vertex V2 is even. So you just keep doing this process, and so since each vertex has even degree, right? Every edge arriving at a vertex, I'll call it V sub k now to put it, kind of make it arbitrary. Every edge that is arriving at some vertex V sub k can be followed by another edge departing from V sub k. I guess the only issue is now I have to figure out what's the end game here. This obviously is not an infinite graph. This isn't going to go on forever interminably. So at some point, we have to run out of edges to work with. Maybe we arrive back eventually at V naught and there's no more edges to use, but yet there were some other edges elsewhere in the graph that we had never touched so far. That could happen, right? So like if you had, so again, this is not part of the proof, guys. I'm just kind of showing you a little example here. If you had something like this, where let's see, how do I want this to look? Yeah, and then you just have some graph over here, right? So you could start here at V naught, go in here for a while, come back and go here and then go here and be back at V naught again, but there might have been some edges over here that you didn't use. Let me make something a little more realistic. How about if I just make a square like this? I'll just kind of draw this in here. Okay, so you start at V naught and you follow the algorithm. Here's your first edge right here. You don't need to write this down. I'm just sort of showing you how this algorithm might proceed. So you do that, and then except this doesn't work because these vertices have odd degree. So let's just make another edge here and another edge here, something like that. Okay. So you've got now all the vertices have even degree. And but what if you did this? You just decide to go around the outside of the square. And then you decide to just go around the rest of that triangle, and now you're back at V naught and you can't leave again, but you didn't hit all the edges yet. So that's what I'm trying to say. So what you may have to do if that happens is go back to your trail that you've been building and insert a sub-cycle within it. So like I might have to come in here and, oh, here's an edge we didn't use. So whenever we visited this vertex, let's add this little edge here, and then I'll go around here, and then over here, and then I'll go around here. And that would take care of some of those other edges that we had not used yet. Remember, you have to use every edge. A trail uses every edge. So if you do this process and you get back to V naught and you can't leave again, and yet there's edges that you haven't covered, then you're going to have to be able to insert sort of a sub-cycle, I'll call it, inside of this graph. So let's write this into here. So what did I want to say about this? So whenever a closed cycle, I don't really need the word closed there, a cycle is closed, but whenever a closed cycle is formed, it can be removed. It can be removed from consideration, so just kind of come up here. It can be removed from our consideration at that point, and we just have to look at what edges are left. So this is going to be leaving a subgraph that is the black edges that have not been traced over yet. Whichever edges those are, that is a subgraph of the original graph. But those black edges are going to be connecting vertices that all still have an even number of black edges incident with them. Okay, every vertex had even degree to begin with. As you're doing this process, that is being preserved because you're entering a vertex and then leaving that vertex immediately. So whatever edges are still left at that vertex, it's an even number. 2 less than it was before, so it's still even. So it's still going to be even. So this is leaving a subgraph of vertices still with even degree. And now you can do one of two things. You can either just say repeat the same procedure on the subgraph. So I'll just do that. Repeat the process on the subgraph. And you might have to do that multiple times, because there could be several of these little closed trails within the subgraph that you have to do that with. But you just repeat that with the subgraph until you have no edges left that you still have to trace over. So you just repeat this process as such. The other way you could finish the argument, if you don't want to just say repeat the process, is you could actually do this as an induction. And you could say, well, now you have a smaller graph, all of whose vertices have even degree. So if you had built up a sort of a proof by induction, you would be assuming that for smaller graphs, right, with fewer edges in them, that this was already a true theorem, right? That's kind of how you could do it by induction. But you can see that it's a little bit of text. It's kind of written out in words here. Yes?
When we're doing the Eulerian trail, can we just do multiple like subgraphs, like subcycles?
Yes, we're gonna do an example and I'll show you how to write this out. Because when I ask you this kind of question, and if the answer is yes, you're gonna want to just exhibit the Eulerian trail to me. And you don't want to get done writing down 25 edges and then realize that you needed to insert some edges somewhere and then have to erase. Well, you can just kind of, I think that's what you're saying. You can just make a little sub cycle around it. I'll show you what that allows you to draw that. So let's do an example. Actually, this is one of those proofs, as wordy as it is, it's more than just a proof. It's an algorithm for how to actually create these Eulerian trails, right? So it's giving you a roadmap of how to, like literally, a roadmap of how to go around on all of these highways and hit every edge. So let's just do one that actually does work. And just practice this algorithm for a moment. Yeah, so we can put a little, is everybody okay if we just end the proof here? Eventually, you have no edges left to trace over, and you've used every edge. So there's really not much else to say. Okay, so let's do an example. So bear with me, I'm gonna draw a fairly messy graph because I want to make sure that there's enough substance to this to make it interesting. So I'm going to start with a vertex A and a vertex B like this, and I'm going to make those connected by 2 edges. Okay. And then I'm going to make another vertex. This one is actually going to be called G. And I'm going to do the same thing from A to G. I'm going to make 2 edges like so. But then I'm also going to connect B to G. So it's going to look like that. And then I'm going to make my vertex C over here on the right, and I'm going to connect A to C. And I'm going to make another vertex D below it, and I'm going to connect C to D. And then I'm going to make another vertex just sort of to the southwest of that, and I'm going to make 2 edges connecting D to E. But E is also gonna connect back up to B. And to another vertex, I'll put it down here, I'm gonna call it F. So E connects with F. And F is gonna connect to both G and to A. And let me just see if I've got everything that I want for my picture. It has to be moderately complicated, just so that it, oh, I am missing something. Oh, I wanna have an edge from D to F as well. There we go. It has to be moderately complicated, just so that the algorithm will be a little bit interesting to do. Okay, and so let's ask this question. Does G have a closed Eulerian trail? That's gonna be the question. Before I actually launch into trying to write one down, it's probably good to use our theorem and just check, does every vertex have even degree? So we can go around, let's just check this out. 1, 2, 3, 4, 5, 6. So vertex A has degree 6. Vertex B has 4 edges incident with it. Vertex C has 2. D has 4. E has 4. F has 4. And G has 4. They all have an even degree. Okay? So they all have even degree. Great. So the answer is already yes by theorem 11.2.2. But then the natural follow-up is going to be to construct one, right? We're going to want to actually construct one. So we need to pick a vertex to start at. I guess I'll pick A. And well, we've got a whole room full of people here. I don't want to do this all by myself. Let's just go around. Sam, I'll start with you. What edge, if I start at A, which edge would you like me to take?
The upper one going to be.
The upper one going to B. Okay, so I'm gonna go from A to B. I'm gonna write that down. I'm gonna color this blue as I'm going along. Now I'm at vertex B. Mason, I'll pick on you next. For B, where do you want me to go? Back to A right away. So I have to go back along this edge. Okay, so I'm gonna go from B back to A again. All right, Andrew, I'm back at A again. Where do you want me to go this time?
G.
To G. Okay, let's go to G. I'll just take this edge right here to G. A goes to G. Tanner, now I'm at G. Where would you like me to go?
Back to B.
Over to B. Okay, so let's go from G to B, right? Every time we enter a vertex, we're also able to leave that vertex because there's an even degree. And even now, vertex A, you know, we've left it for the third time, but for the second time, we're gonna be able to come back to it again, right? There's always an edge to come back. Okay, Marcus, I'm at B. Where do you want me to go next?
E.
I guess I have to go to E. I don't have a choice. I have to go to E. Great, so let's go to E. All right, Fong, from E, where should I go next?
E from G.
To G? I can't go from E to G.
Oh, E from.
From this one
Okay,
to F?
Yeah.
Okay, E to F, I like that. Excellent.
I see.
The only way you can mess this up, guys, is you put something that's not actually an edge. Okay, otherwise, really, there is no right or wrong. What you guys are telling me is all perfectly correct. Vivian, I'm standing at F. Where should I go next?
Back to A.
Back to A again. All right, we're going back to A already. So let's go back to A. I'll put A there, and I'm going to continue on to my next line. So now that I'm at A, I need, let's see. I'm suddenly blanking on your name. Starts with an A. Ashley, that's right. Go ahead.
A to C.
A to C. Yes, let's go from A to C. So there we go. A to C, like so. Now I'm at C. And Jean, where do you want me to go from C? To D, right? It's the only place I can go. And let's see, from D, where do you want me to go? You have some choices. Which one? To E. Okay, let's go to E. All right, sounds good to me. Kevin, now that I'm at E, where would you like me to go? I have to go back to D, exactly. So go back to D. Now I'm standing at D, and Alyssa, where would you like me to go from D? To F, pretty much have to do that. Okay, and now from F Kyle, where would you like me to go?
G.
To G. All right, have to go there. And finally, Jose, from G, where would you like me to go? I have to. Actually, I had the exact right number of edges for everybody to get one in. You guys played too nice. We didn't have to insert any cycles into it. We actually used all the edges without having to do that. If we had been just really going after A every single time from the beginning, we could have ended up back at A with no way to leave again, with some other edges still to be done. And if that happened, you'd need to go back in and insert. So if you needed to insert a subcycle, and this is what Jose was talking about earlier, you could do something like this. You know, you could put some extra edges like this, and that would create like a little cycle within the big cycle, rather than like starting all over to write the whole thing out again. I would understand what you meant by something like that. So that's totally okay. Okay, questions? Yeah.
Yeah, so what I was saying is like, can we have like see how there's so many cycles here?
Yeah.
And we just know all the cycles down, that be enough or not?
You mean the cycles within this graph?
Yeah.
No, you need to see how they're all put together, right? Into like one big closed Eulerian trail. So if you just identify as individual cycles, it might not be clear how to actually paste them together into, there might not be a unique way of pasting those together. So I think it's better to actually have the whole cycle in one sort of string of edges like this. Yeah, Marcus.
And if you do miss one or
Uh-huh.
miss a couple, like you're always gonna get specifically cycles left over.
Yes, you would have to be able to get cycles left over that you could then fill in with. That's true. Yeah. Mhm. Because all of those remaining, whatever those black edges were that are still there that you need to fill in, they are all connecting vertices that have only an even number of black edges left. So you're gonna be able to enter and leave, enter and leave, enter and leave all day long. Eventually, you gotta get back to where that edge where you started again. Yeah, so that's that. This is one of those things that's sort of foolproof. Like you can't really do this wrong. You know, you might have to do the insertions of subcycles and stuff like that, but it's gonna work if you're willing to just see the process through. Yeah, Sam.
If these were more complicated, like a lot more edges and a lot more nodes,
Uh-huh.
would you, like, is there another approach to this, or would you just like put it in a computer?
I'd probably go to the computer at that point. Yeah, because there is really, you see, all I'm doing is tracing it out with markers. If I had like 50 edges incident with every vertex and I had a massive, messy, crazy connections like that, yeah, just like any other physical problem, you would want to put it onto a computer. It's like if I'm my last class, I was teaching students how to find eigenvalues of a matrix. Well, they were all very small. If the matrix was 20 by 20, I would have said, put it into a computer. Yeah, definitely. Okay, guys, there is anything else? These are great questions. There's a companion result that addresses open Eulerian trails. I'm just gonna put that down as well. It's not anything too surprising. 11.2.3. The very next theorem in the book just says that with G as before, so meaning it's still a connected general graph of any kind, G has an open Eulerian trail if and only if G has exactly 2 vertices of odd degree. So now it is okay to have odd degree vertices, but it has to be exactly 2. And those 2 odd degree vertices will have to be the start and finish of your open trail. So an open trail is just one that doesn't begin and end at the same point. You're still following every edge, but so let me just add that here, guys. The word open just means you have a different start / finish vertex. So you start and end in two different places. But maybe you still want to hit every single one of these edges exactly once. Excuse me, so let's maybe, before we write down the proof of this, I'm just gonna show an example of this kind of a scenario that could come up. I'll make it a pretty small graph, guys. I'm gonna have a graph of order 5. I'm gonna make a square and I'm gonna put a vertex in the center of that square. And I'm going to connect all 4 corners to that center. But then I'm also going to make a multiple edge going across the figure like so. So if we take a graph like this, let's label the vertices A, B, C, D, and E. E is in the center. And if we take a look at the degree of each vertex, A has degree 3, B has degree 4, C has degree 4, E has degree 3, sorry, D has degree 3, and E has degree 6. So on this graph, which is a multi-graph, we have exactly 2 vertices of odd degree. So according to our theorem, there should be an open Eulerian trail. And because the 2 vertices have the odd degree are A and D, that's gonna be where we start and finish this trail. Doesn't really matter which one we start at, but let's see if we can exhibit an open Eulerian trail here. I'll do the same thing we did on the last example. We'll just lay out a list of edges here. Should be pretty straightforward. So that worked pretty well to call on you guys. Why don't we do that again? Let me just go in the opposite order. So Jose, why don't you tell me, where do you want to start from?
8.
A, and you want to go to E first. Okay, so we're gonna go from A to E. Okay, now notice he picked an odd degree vertex. You have to do that. So the start and finish vertex would have to be odd degree. Okay, all right, Kyle, I'm at E. Where do you want to go? Okay, we'll go to D, which is straight across here. Great, so we're gonna go to D. All right, Alyssa, from D, where should I go next? Up to B. All right, we'll go up to B here. So D goes to B, and now Kevin, where would you like to go from B? Back to E again, in the center. All right, we'll go back to the center, which is E. And Litzy, from E, where would you like me to go next?
C.
Over to C. All right, we'll go down to C here. And now Jean, from C, where would you like to go?
E.
Back to E again. All right. Go back to E again. And Ashley, from E, based on what this is why you have to have them colored in, because you can see we've used quite a few of those edges. Where are you gonna need to go now?
Back to B.
Absolutely, it's the only edge left out of E. So I'll go back to B. All right, and then Vivian, now I'm at B, where can I go? This is supposed to be colored in here. Yeah, so the only black edge left is going back to A right there. Okay, so now we're back to A again. Okay, Fong, where should we go next?
C.
Yep, we go from A straight down to C, exactly. So I'll just put C here. And once I'm at C, Andrew, where do you want to go from C?
D.
To D. I have to go to D. And is that everything?
Yes.
Yeah, we cannot leave D again, and we've hit every edge along the way. So yeah, so that's a good example of an open Eulerian trail. Let's write down the proof of our theorem here. It's actually pretty easy to prove this because we have the other theorem that we can take advantage of. So I'm gonna go ahead and show you how this works, and we might even talk about it in the context of the example we just did. So let's do the forwards direction proof first of all. Let's assume that G has an open Eulerian trail. Assume G has open Eulerian trail, right? And I want to show that G has exactly 2 vertices of odd degree. So we've got this open Eulerian trail here. We've even got one on the board for this example. Does anybody have any thoughts what we could do to take advantage of the theorem we already proved? So I unfortunately have erased it. It's the one that just says that there's a closed Eulerian trail if and only if every vertex has even degree. So I've got this open Eulerian trail. Let's actually be precise. Let's say starting at X and ending at Y. So, and X, by the way, is a vertex in V, Y is some other vertex in V. So these are two vertices, X and Y. What could we maybe do to, we don't have a closed Eulerian trail, but we have an open one. Could we somehow make a closed one? That we could then use the theorem for? So this is not closed, but could I take this trail and make it closed, Sam?
So, like, cases and have all the names.
We don't know right now, because all we're assuming is we have an open Eulerian trail, so we don't know that the vertices are all of even degree yet. We're kind of trying to prove something about those vertices. Jose?
I mean, if the open learning trails are even, this would imply that some of them are odd, right? Because if we're not,
We're not leaving,
Yeah.
we're entering vertex D, but we didn't leave it again.
yeah,
So that has to be odd. Same thing with A. You could certainly write that out as an argument, but I want to just do something even easier that will leverage the last theorem, right? So what I'm gonna suggest we do, unless that's a hand. Oh, sorry.
I was gonna say only use the vertices with even degree.
Well, we do have to visit these odd
We
degree
do start to
vertices, like
miss
the
them, okay.
vertex A shows up in the
Okay.
middle of the trail a little bit.
Take away edges.
How about, you're on the right track, Alyssa? Adding
Oh, okay.
edges, yeah.
Oh.
Let's just add, is that what you're gonna say?
yeah.
Yeah, just add this edge that connects these two vertices of odd degree, and then use it to sort of close up your trail, right? So you can take that dotted edge and add it to the graph. So add the edge, I'll call it YX, to the edges of the graph, so we'll add that to E. And use it to create a closed Eulerian trail. In the new graph. It's technically not the same graph now, because we've added an edge to it. So we've made a new graph where we added this edge. And because every vertex has, well, because it's a closed Eulerian trail, that means now every vertex has even degree. Okay? So in this new graph, every vertex has even degree. Let me get my camera over here so people can see that. So in this new graph, every vertex has even degree, and that's by the previous theorem, theorem 11.2.2. Okay, every vertex has even degree. Now just remove the edge again. Take the edge back out. As soon as you take that edge back out, those two vertices, which would be X and Y, lose 1 degree each, which drops their degree back to odd. Okay, so now removing the edge YX leaves only X and Y with odd degree. Subtract 1. You just subtract 1 from the degree of both of the vertices X and Y, and both of them have odd degree. That's 2 vertices. That proves we have exactly two vertices of odd degree. Makes some sense? Okay. So it's pretty easy once you just use the previous theorem to prove this one. And I'm gonna do the backwards direction by the same idea. I'm gonna start with exactly 2 vertices of odd degree. Yeah, let me just give the overview of it first. I take my graph with 2 vertices of odd degree. I'm gonna add the edge between those 2 vertices. That will then leave us a graph where every vertex has even degree. I'll therefore have a closed Eulerian trail by the previous theorem. And then as soon as I remove that edge back out again, it opens the trail. And you have your open Eulerian trail. Seem reasonable? Just have to write it down. Yeah, this is one of those days people are looking at some of these proofs, they're like, this doesn't look like a math class. There's a lot of words we have to spell out here. But it's mostly just kind of common sense that we're talking about. Okay, so let's assume G has exactly 2 vertices of odd degree. Say X and Y. And let's add the edge XY to the graph. So we'll add one edge that wasn't already there. There might already be an edge between X and Y. So if that's the case, then we're just adding another edge. Okay, so just to be clear, these 2 vertices, they have odd degree. It doesn't mean that they can't have an edge between them. But because we're allowed to use a multi-graph here, there's nothing wrong with adding this edge again if it's already there. Okay, so we do that, now every vertex has even degree. Okay, so now each vertex in G has even degree. So there exists, each vertex has even degree, so there exists a closed Eulerian trail. And again, that is by the theorem 11.2.2. So we have a closed Eulerian trail here. And now I'm just gonna take that edge back out. And that opens up the trail. You're still using every edge that's left, but now you'll have a starting and a finishing vertex at X and Y. So now removing the edge XY leaves an open Eulerian trail. That's it. And that open Eulerian trail will, because you broke the closed trail with that edge from X to Y, those 2 vertices are where you'll have to start and finish. That's not really part of the statement of the theorem, but it would definitely be true. Okay. Good enough? You can't really mess this up. If I asked you whether the open or closed Eulerian trails, you're just going to look at the degrees of the vertices. By the way, you can't have both. You can't have both an open and a closed Eulerian trail because the conditions on the vertices can't both be true. You can't have exactly 2 vertices of odd degree and also have no vertices of odd degree, right? So you might have one or the other, or you could have neither, but you could then draw this trail by just following the algorithm as we kind of practiced it here. Any questions on that? Okay, I think it's actually a pretty easy thing. I don't think you guys will be too frightened by it. But I'm going to change the conversation now to something that's significantly harder. And that is the goal of trying to visit every vertex exactly one time. So instead of trying to trace out all the edges, we don't care about that anymore. We just want to go to every vertex exactly once and we don't want to repeat a vertex. So this is the next section, and this one, I will just tell you right now, there is no theorem and there is still research being done to this day on answering this question. Like, this is a deep, deep question. So we'll have some results that we can use and we'll write them down, but they are not going to be two-way results. So if anybody's looking to do research in combinatorics and you're looking for problems to solve, this is gonna be a topic that is a very hot topic in combinatorics. So it is called something, 11.3, this is called Hamilton paths and cycles. So we will have to scratch our heads a little bit more when we're trying to work on this topic here. Let me just recall again, so I was talking about trails over there, now I'm talking about paths, so let's just get clear about what this is. Just recall, guys, that a path is a walk. A path is a walk that has no repeated vertices. Okay, so when we wrote down all of the generic lingo last week, we were talking about walks and then paths and then trails. So a trail is not allowed to repeat any edges. A path is not allowed to repeat any vertices more than once. Now, of course, if it's a closed path, you're going to come back to the first vertex again at the end, and that's not counted as a repeat of that vertex in that case, because you've just kind of arrived back where you started. So you could have, I'll just remind you here, a closed path. That is possible. A closed path is, we call this a cycle. So just to get the word back up on the board, it would be a cycle in that case. So let's write down the definition of what a Hamilton path or cycle would be. I've already kind of explained it, but a path, so definition, a path or a cycle, I'm going to kind of talk about them both at the same time here. A path or cycle which visits every vertex of a graph exactly once. Not more than once, so we're not allowed to repeat vertices, but now we actually want to visit every vertex of the graph exactly once. This is called a Hamilton path or cycle. A Hamilton path or cycle. So let's just, before we get too deep here, let's just have an example to look at. And I get the intuition going, and it can be confusing, having just talked about Eulerian trails, that now we're playing a different game. We're not worried in this context, we don't care about using all the edges, we just want to visit every vertex. So I made up a little graph here, guys. This one's not too big. I'm just going to draw 9 vertices into a little 3x3 grid. Just make 9 vertices here. And what I'm going to do is kind of draw all of the outside of the big square and make that all into a giant square of edges. And then I'm going to do every possible crisscross. I'm going to go horizontally, I'm going to go vertically, and I'm going to go diagonally, crisscrossing through that central vertex a bunch of times. Okay, and that's the whole graph. And I'll label the vertices like I like to do. The first row, A, B, C. And then on the second row, D, E, F. And then on the third row, G, H, and I. So A, B, C, D, E, F, G, H, I. By the way, you'll notice that there's tons of vertices of odd degree here. So this graph has no Eulerian trails, open or closed, right? Degree 3, degree 3, degree 3, degree 3. That's way too many, right? So just as a quick remark, since we were just talking about it, there are no Eulerian trails here at all. No Eulerian trails, that's just based on those very easy theorems that we just went over. But now the question is, can we build a path or a cycle that visits every vertex exactly once? By the way, if you make a cycle that is a Hamilton cycle, that is also a Hamilton path, because you can just, again, get to the last vertex and stop without going back to the first vertex again. If you don't want it to be a closed path, you can leave it as an open path, and that would be a Hamilton path as well. So if you have a Hamilton cycle, you also have a Hamilton path, but not necessarily the other way around. Yeah. So can we give one here? So let's just see, does this graph have a Hamilton? Let's try to be greedy and go for a cycle. Let's see if we can get the cycle, then we know we can get a path, right? So we have to visit every vertex exactly once and then find our way back to the starting point. So, is that a hand?
Well, I had a suggestion.
Oh, I would love to hear it, please.
I say you start at E and then you just go out to the side and then you go around.
And then come back to E again. Sounds like a great way to do it to me. So that's perfectly good. You can start with E. So the answer here is going to be yes. And I'm just going to exhibit this for you. So I start at E and I'll just go out to B, I guess, it's just straight above me here. And I'll just go around the outside perimeter of the whole thing. So B goes to C, goes to F, goes to I, goes to H, goes to G, goes to D, goes to A, and then back to E again. That would certainly work just fine. Okay, so you can certainly do it that way. There'll be a million other ways to do it, of course. So this is not unique by any means. But we were certainly able to do it. Okay. I wish there was just some nice theorem that would tell us whether we would have these Hamilton cycles or paths or not, but there just isn't just a one single catch-all result. I can draw you a very simple example where things kind of don't work out easily. So if I just I'm gonna make one more graph, guys, just to show you an illustration here of what can go wrong. Let's make a square just with 4 vertices. I will put another vertex in the center again, but this time I'm only going to draw the diagonals kind of going out from the lower left to the upper right. And I'll label the vertices again, A, B, C, D, and E, like I did before. But what I claim is that so the claim is there is no Hamilton cycle. It's kind of interesting. There's no Hamilton cycle, but it's a very, very obvious Hamilton path. A, B, C, D, E. Okay, so you can get, just as a side remark, there is a Hamilton path here. The Hamilton path, and there's more than one, but I'll just pick the one that's kind of alphabetical. A goes to B, goes to C, goes to D, goes to E. And in this case, of course, there are edges that I didn't use. I did not use the edge from B to E, and I did not use the edge from A to D, right? So I'm not using all the edges. I don't care about that anymore. I just want to visit every vertex. So this would be an example of a Hamilton path, but somehow there is no Hamilton cycle. Let's try to understand why that is and see if we can make some observations about Hamilton cycles that would have to be true. Again, because you're trying to build a full cycle, you have to enter a vertex and then also be able to leave it again. Which means that your cycle is going to have to use 2 of the edges that are incident with each vertex. So when you visit this vertex, You have to be able to get in there and you have to be able to get out of there. Right? Because it goes on. It does, you don't stop. If it was a Hamilton path, I'd say, yeah, you might stop at the last vertex. But for a cycle, when you enter a vertex, you then have to leave that vertex again. And as soon as you have visited that vertex, you're never gonna visit that vertex again. Which means all of the other edges that might be around that vertex are discarded. You cannot use them. Right, so in this case, for example, what we could say is, so let's try to do the proof of the claim. I'm gonna do this kind of in almost conversational style a little bit. But the proof that there's no Hamilton cycle. For example, such a Hamilton cycle must use the edges that I'm gonna list right now. I'm gonna list some edges that you have to use. So you see, you're gonna visit vertex A. So your cycle has to use both of those edges. You have to use DA and you have to use AB. Maybe while I'm at it, I'll start shading them in a little bit. I have to use this edge and I have to use this edge if I'm talking about a Hamilton cycle. Because I've got to visit vertex A and I've got to get in there and I got to get out of there. But I also have to do the same thing for C. Right? C also has low degree. There's only two edges there. You've got to use both of them. So B goes to C and C goes to D. This has to be used as well. You must use that edge as well. So I will go ahead and shade in the edge from B to C and the edge from C to D. Now, if vertex E wasn't there, we would be good to go. We would have our Hamilton cycle visiting all of those other vertices. But we also, to visit vertex E, we would also have to use edge BE and DE. So actually, you would end up with this situation where everything is blue. And what's the contradiction here is that how can you use three edges that are incident with D, for example? You cannot, because you're going to enter D and leave D once. That means there can only be two blue edges with each vertex. Right? Does that sound good? So this is too many edges that are forced. You are forced to use all of these edges. Okay, so using all of these edges, let me call them forced edges, because I will use that word from time to time. Using all of these forced edges involves more than two edges incident with D, or we could have made the same argument for B. So that's more than two edges incident with D or B, which is a contradiction. You cannot use more than two. You cannot use more than two edges that are incident with a particular vertex. Your Hamilton path, or your Hamilton cycle cannot use more than two of those edges. Does that sound right? Seem reasonable? Okay, so, this was a very small graph, so it's kind of easy to figure out that it's not going to be possible. Let me make some general observations though, because these observations will help us when we have more complicated graphs, I think. And so I have a list here of just a few observations that will help us with analyzing these. I've kind of said some of these things already, but I just like to get them written down. You notice what's not been going on the board lately? A theorem, a nice result that tells us, oh, here's when you're gonna have a Hamilton cycle. This is just like some general observations, right? So here we go. For each vertex, I'll call it little v in capital V, right? Exactly two edges that are incident with V will be used by a Hamilton cycle. If I'm gonna have a Hamilton cycle, I have to use exactly two of those edges that are incident with V. And that's because you're gonna enter and leave that vertex, yeah. Once you've used those two edges, all other edges that are incident with V should be discarded. They're no longer, they're pretty much off limits, right? Because you cannot revisit those vertices again. So let's add that as well. Once two edges have already been used, no other edges. But once two edges have already been used, no other edges incident with V may be used. Okay. And then I'll make one more observation here. By the way, all of these observations are going to help us rule out a Hamilton cycle. These are things that limit us. These are things that make it impossible to complete one of these Hamilton cycles if you apply all of these observations. So here's another one. Here's another one, guys. A Hamilton cycle cannot contain what I'm going to call a premature subcycle. A Hamilton cycle cannot contain a premature subcycle. By premature subcycle, what I mean is this would be a cycle that fails to reach all of the vertices. It's a cycle, so this is a cycle that fails to visit every vertex. This is a really powerful one. This is a really powerful one. So like if I am forced to create a premature subcycle, let's look back at this example over here again. If I go back to this example and I make everything black edges again, I'll just show you real quick here. So I go here, right? So here's A, B, C, D, E, right? And I'm gonna try to make a Hamilton cycle right now. So I start, let's say I start at A. I know I have to visit A. That's one of the vertices. So I'm gonna be there at some point in the cycle and I'm gonna have to leave A. So let's just go over to B here, right? And then from B, maybe I decide to go to E, right? And then I have to leave E, so I'll go down to D, right? And if I go back to A right now, this is a premature subcycle that has not visited E yet. And by the way, this is force on us. But would everybody agree that all four of those blue edges would have to be used? If you want to visit vertex A and then leave it, you've got two edges to do it on. You got to use them. Same thing with E. You got to enter and leave E. So those are all required edges. But how are you going to visit C? You have not completed the Hamilton cycle yet because you have not visited C. And you can't really add it on. To try to add it on to what's already here, you're going to create another visit to one of these vertices that's already done, right? You can't go back to any of these other vertices in order to get to or from C. So this is the point of what I'm saying here, is that your Hamilton cycle cannot have a premature subcycle. That's kind of what we're saying. And that's often the way you're going to get contradictions. I'm going to give you guys some pretty big graphs. Not today probably, but I'm gonna give you some graphs with a lot of vertices and you're gonna have to start tracing through, there's gonna be cases. You'll have to say, well, if I use this edge or I don't use that edge, right? And it will take a little bit of work, but the thing that usually is where the rubber hits the road on the contradiction is that you forced yourself to make a subcycle that is premature, that is somehow missing a vertex. So that's kind of a neat thing to ultimately that comes out of this whole thing. Almost everything I'm saying here on the board right now are going to be observations that will help us to say, no, there is no Hamilton cycle. You might be wondering, is there anything that would allow us to say yes? You know, is there anything that would just give us an automatic yes? Like this graph, you know, have one. Is there something that should have given it away that it would have a Hamilton cycle? As I've been saying, guys, this is a pretty open area that has not really gotten that developed in terms of research. It's an active research area to try to come up with conditions that will guarantee or which will completely rule out the existence of these kinds of cycles. We have these sort of half-hearted observations that might help, but nothing is like a smoking gun to say, yep, that's definitely not going to have a Hamilton cycle, or that definitely will have a Hamilton cycle. You sort of have to get in the trenches and just try to make something. There is one theorem that does guarantee a Hamilton cycle. Well, there's actually a number of them out there, but there is one that's sort of fairly famous that I'd like to write down. And I'm not going to prove it though. It's not easy to, a lot of these results are not easy to prove, but I'm going to give you one theorem that is a yes on this question. So if you've been wondering, when are we going to get to a theorem in this section? There are not many, but I do have one for you here. And it is the following. It says this: if G has the Ore property, I have to explain that. If G has the Ore property, that's O-R-E, then G has a Hamilton cycle. And actually, the graph that's on the board here does not have the Ore property, but it still has a Hamilton cycle. This is not an if and only if theorem. What is this Ore property that I'm talking about? It's kind of a weirdo property. I'll just write it down and then we're just about done for today. So the Ore property, this is, everybody's waiting with bated breath. What could it possibly be that would allow us to say that, yes, we have a Hamilton cycle? What it is for all pairs, I'll say it this way, for all pairs of distinct vertices, I'll call them X and Y in the vertex set V. So this is a property that may or may not be true. So all pairs of distinct vertices X and Y in V that are not adjacent. That's weird. That are not adjacent. So that means they're not connected to each other. So if it's the case that the degree of X plus the degree of Y, if that degree is big enough, if it is at least the order of G, then the Ore property holds. So if you take your graph, like here's an example, A and D are not adjacent. If we add up their degrees, that's 3 plus 3, which is 6. Is 6 greater than or equal to the number of vertices? No. So there's a counterexample to this property. This graph does not have the Ore property. But if a graph has this ORA property, then it is guaranteed to have a Hamilton cycle. Guys, the intuition here is that you need if you want to make a Hamilton cycle, first of all, you need vertices with big degrees. You want to have lots of edges to play with, right? To get in and out of vertices. You need vertices with big degrees. And you don't want them all clustered up right next to each other. You want them to be non-adjacent. So you want them to kind of be far apart in the graph so that you've got lots of edges spread out through the graph. If you have that kind of a graph, you are more likely to be able to successfully trace your way through a Hamilton cycle, right? This is not a good graph. This graph does not have vertices of very big degree at all. They're so small. Right, vertices of degree 2 are really, really bad because you're forced to use those edges. And when you're forced to do things, you often get premature subcycles. So I'm already a little past time. I'm gonna stop there. We'll do some more talk and examples on this. We'll actually do a group work next time and practice trying to create Hamilton cycles. It's a fun subject. I like it. Everybody good? Oh, I always feel so much better after I get done talking about graph theory than when I started. So I'm glad you guys were here. Thanks for coming today, guys.